Okay, I'm back. In the context of OpenCL, even if we parallelize these, we still have to treat each of these individually. And so, like this, this 1 plus 5 equals 6, right? That one specific operation out of these four, that is going to be called a work item. Right, 1 plus 5 is 6, that's one work item. There are several, potential work items here. We are going to call these a work group. So in this case, it's 4 work items per work group. These sort of execute on a single compute unit, and these sort of dimensions are going to have to be fixed when we launch the kernel, which is the next part of this. The kernel is a function which is going to sort of tell us how each work item is going to be executed. In this case, right, we're doing addition, so 1 plus 5 is 6. Easy enough. Could be multiplication, so the kernel is going to be different. We have to multiply them. It could be matrix multiplication, which is completely different, right? Could be doing dot products, could be doing all sorts of crazy stuff. And so, right, just to, overview, kernel determines how the work items get executed. The kernel is sort of contained within a program. A program is OpenCL source code, which, contains, let me get it straight. The program contains the source code for one or more kernels. Like I mentioned, right, you could do addition, multiplication, division. Those would all require different kernels. And so the program sort of houses all of that. The two high-level organizational topics involved in this are going to be the context and the command queue. Context. Queue. If you want to think about this in terms of cooking, just as a preface, I know my handwriting is bad. Look, in school, I have not had to pick up a pencil in months. My writing has atrophied so much. At one point, I swear to you, it was good. Right now, it's cooked. Back to what I was saying. The context, if you're thinking about this in terms of sort of cooking, where, the food you're making is just like the work items, your context is your kitchen. Your context will sort of determine what tools you have access to. So that could be a CPU, a GPU, it could be multiple GPUs. It determines your memory objects, which we'll get into in a sec, and your programs that you can run. Your command queue is a queue, like the name suggests. That is a data structure which is first in, first out, which means the first command that gets submitted is the first one that's run. It submits those commands to devices which are in the context. So when you initialize your context, you have to specify which device you're going to use. And you use the queue to submit commands to those devices, and that will, execute your program. Now, let me get water for a sec. That Chipotle burrito messed me up a little bit. You might be looking at all of this and thinking, okay, well, there's, some inherent danger here, right? Because you're accessing multiple points in memory at the same time. At the same time is crazy because, you think before we're doing this sequentially, you access this, and then that, you compute that's fine. You work on the next thing, that's fine. When you access multiple things concurrently, you can run into thread safety issues, potentially, where you might access something that's being written to at the same time, you get a race condition, horrible stuff happens. OpenCL has some aspects which try to make this safe. So, for example, each of these work items that I mentioned is isolated in its own environment. And as a result, there are these sort of distinct memory spaces that you can work with. So, each work item is going to have its own private memory. So it's a small block of memory that only belongs to that work item. There is local memory, there's local memory, which is visible to this entire work group. And then there's global memory, which is visible to the entire kernel. Private, local, global, these are things that we're going to see again when we go to actually write our kernels. That's pretty complicated. That was a lot of concepts really quickly. And looking at all of this does look like a lot of overhead. Understandable. It is. You pay a very high upfront cost with setting all of this up. But, you're probably wondering to yourself, why would this be useful? And, if you're just doing 4 items here, it's not. But, I mentioned that 10,000 by 10,000 array or matrix before, then it is useful because the high upfront cost you're going to pay when setting all this up is going to be outweighed by the fact that you are going to be able to compute the work items so much faster using a GPU when you have to do that huge array, that it's going to be worth doing this. And so now let's get into the implementation.